Video lesson 10.3, area of a circle and area of a sector. So when we're dealing with areas, a lot of times we're dealing with circles or parts of a circle. So we've discussed in the past circle formula. So I have that here, area equals pi r squared. That's an important one to make sure that you know. So you have it right here. But that's dealing with all of the circles, the space that inside of the circle, how much it takes up. So when dealing with this, now there's some other important information that you should know too, and that is dealing with the area of a circle, is that sometimes you might need the equation of a circle. So you may or may not have seen this one before, but if you have not, I want to introduce you to now, and we will be talking in more depth about the circle formula, the equation of a circle, I should say, at a later date in units 13 and 14. But again, just to kind of give you a brief knowledge of it right now, this is the form that you'll see it in, where H and K represent the center of a circle, and R is the radius. So if we were, for us right now in this unit, we're really just dealing with the R part, being able to isolate it. And so if it's R squared is the information that we're given, we could take the square root of that, and that would give us the R value, aka the radius, so that we could plug it into the formula and find the area of the circle. So they do like to sometimes utilize this formula to give you the information. Like I said, we'll get into more detail specifically about the circle itself, and what the H and the K represent and how we can kind of use that or derive this. But for now, just our important thing is to note that I have this R squared term right here, and I can get R by just simply taking the square root. We can see that in the first example here. So I know that here I have the equation of a circle. So again, you can identify that you have a circle based on the equation. Again, this is technically the H and the K value, which represent the center of the circle. But for now, because all we need to know and figure out is the area of the circle, I just need this information here. We know that this is R squared, right? So R squared is 36 in this case. So if we take the square root of both sides, we'll get R is 6. So that gives us the R value. Now, when dealing with the area of a circle, the good news is I actually just need the R squared already. So area equals pi r squared. So the fact that we have r squared already given to us in that form, I don't even need to take the square root. Just knowing that r squared is 36 is enough for us. So area is going to be pi times 36. So in this case, that's just 36 pi. All right. Again, if we needed to know the decimal value, we could approximate that by plugging into the calculator and finding out what 36 times pi is. But again, for this one, it just simply says the area, doesn't tell us to round or anything. So leaving it in terms of pi is perfectly acceptable. So again, important to know is that this is your r squared term. If I do need to find r itself, we could just simply take the square root. Otherwise, but for this specific formula, r squared is what we need. So I can just simply take whatever that value is, plug it in, and simplify. All right, look at example number 2. In this case, very similar to ones that we had done in unit 10.1, which was composite areas, taking a figure, so in this case a rectangle, and an additional figure and adding it to it. So I've got a rectangle and a semicircle being put together to create this new shape. So they want the total area here. So they're looking for what the total area of the shape is. So I want to find the area of the rectangle, and I also want to find the area of the semicircle, and I can add those together. So again, I like to kind of make a little statement off to the side so I can remember what to do. So area of the whole figure, so I'm just going to write area of the figure equals, and we're going to have area of the rectangle plus area of, in this case, the semicircle. So off to the side here, area of the rectangle is going to equal length times width. It's a formula we need to know. In this case, my length in this case is L, which is 10. My width here is W, which is 8. So I've got 10 times 8. So I've got an area of 80, and this is inches squared. So that's going to be my first part. So area of the figure is going to be 80 plus, and I got to figure out the area of this semicircle. All right, so that's all of this. Again, semicircle is just half of the circle. So area of a semicircle is going to equal pi r squared. And again, I'm taking half of that because I'm dealing with only a semicircle. So in this case, 1/2 pi, and I got to figure out r. Now, again, r is the radius. So that's from here, the center of the circle, out to the edge. So that's going to be this part right here. So again, the whole thing is 8 because the rectangle, this whole thing has to be 8 also. So all of this is 8. So that means that just this part over here is going to be 4. So that makes my radius 4, which I can square. So that's going to be 1/2 pi times 16. All right, and half of 16 is 8, so that's 8 pi. So that's going to be my area of the semicircle. So I can come up here, 8 pi. Once again, if they don't tell me to round, I can't physically add these numbers together. This would be my answer, right? If I can't actually add them together, that would be in terms of pi, right? Now, if I do want to add them together, or they tell me I can round them, then we're just going to plug in our calculator, 80 plus 8 and pi. Again, we're going to use the pi button for that, and as a number, that comes out to 105.13274, blah, 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 blah. And again, like I said, if they're doing this, they're going to tell you to round to something. For this case, I'm going to say it's approximately 105.1. And again, it's inches here, so inches squared, because we're talking about an area. So again, if the question is asking you to round, obviously we're going to round. If not, the original answer that I put up there in terms of pi would be the correct answer. All right, so moving on to the next one. Here, we got another area of a shaded region question. Again, just like similar to the first lesson in this unit. But it's a little bit more involved, right? We did a couple things like this, but maybe not as advanced. Here I've got a inscribed triangle, so we do have to, be cautious of some information. Again, we have inscribed. That's something that we talked about earlier in the year. What does it mean? It means that all the points of in this case, the triangle, are touching the edge of the circle. So that gives us some information. It also allows us to kind of like interpret things based on what we know. So let's label some stuff here. So I got a radius here of m, so m is right here, so that's 13. The length of BC, that's this part over here, right? They gave me that as 24, all right? And I got to find the area. So again, the thing that we need to know is that when I have an inscribed angle, which is this one right here, angle B, when it's inscribed to a diameter, which is all of this is always going to be a right angle, right? So AKA, if I have a triangle, make a better one there. If I have a triangle, right, inscribed in the circle, and one side is a diameter, the angle across from it, in this case, angle B, is always going to be a 90-degree angle. Like I said, we're going to talk more about circles later on in more depth, but an inscribed angle is half of its arc, and this arc would be 180, which is the reason for it to be 90, but we'll get into that in more detail later on. So for right now, all you need to know is that if you have an inscribed triangle and one side is a diameter, then that angle across from it will always be 90 degrees. So if that's 90 degrees, that means I have a right triangle here. So to find the area of this shaded region, so area of the shaded, that was a little sloppy, is going to equal the area of the circle minus the area of the triangle. All right. So area of the circle part, not too bad because we know the radius. So area of the circle is equal to pi r squared. So pi times the radius, which was 13. So that's going to be 13 squared, which is 169. So 169 pi. So that part was fine. No issues there. Again, I'm going to leave it in terms of pi. Even though they tell me to round, I'm going to do that at the very, very end. So the next part is area of the triangle, which again, we know the formula is 1/2 base times height, which is fine. The problem here is, what's my base and what's my height? Well, I've got the base part here, right? Because the base and the height always have to make a right angle with each other. So I've got this part here. That's 24. right? The part that I'm missing or that I don't know is this part over here, AB. That would be my height in this example. So I got to find that part. So we got to get a little creative here. I don't have angle measures per se, so I can't use any trig to find it, which sometimes they do give you information like that, and you can use trig to find the pieces. But I don't. But I do know that the radius is 13, so I know that this side is also 13. So all of this is 26. So now I have one side of the right triangle, which aka the hypotenuse. I have a second side of the right triangle, which one of the legs is 24. So I can find the third piece, or the other leg, by using Pythagorean theorem. So a squared plus b squared equals c squared. We'll call this x for a moment. So x squared plus 24 squared has to equal 26 squared. All right, so I'm going to plug those values in and then simplify them. So I got x squared plus 24 squared is 576 equals 26 squared is 676. All right, if I subtract those values, I get x squared is 100. And if I take the square root of both of those, I get x to be 10. So now I know that this AB is actually 10. So that's my now height for this figure. So we're going to plug this back in. So I got 1/2. We've got the base, which we said was 24. We've got the height, which we just found to be 10. Now I can calculate this from here if you want to make that easier. 1/2 of 24 is 12. 12 times 10 is 120. All right. Or you can use a calculator, but that's what I'm now subtracting from my 169 pi. Now, be careful. You cannot subtract 169 and 120, right? They're not like terms right now because this has pi. So I have to actually multiply this by pi. So again, if you told me it didn't tell me to round, this is where I would be over. I would stop here, right? But we do have, in fact, instructions that says to round to the nearest whole number. So I'm going to actually plug this into my calculator and find out what this is. So let's do it in pieces here just so you guys can follow along. So 169 pi is 530.9291585, blah, 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 blah. I'm going to subtract the 120 from that. So when I do that, that gets me a value of, was that 410.9291585. And now I can round off to what they told me to, which is the nearest whole number. So that means it's approximately 411. And again, our units here, they gave us, they didn't give us any units. So we're just going to simply say units squared. So a lot went on in this question, right? But again, it's not over the top. It's not crazy, but you just got to be careful about the little pieces and sometimes having to find extra information that goes along with it. All right, example 4. Now, I'll be honest with you. This question is quite advanced at this. So I think I'm going to hold off on this one until we see, because the Regents exam likelihood of something like this is extreme. But this question would require you to use some trig in order to find this. So basic concept would just be like if I was to drop an altitude here, right? We know that that would make it 90 degrees. And if it's an altitude of an isosceles triangle, then we've got two angles being divided here. So you get 20 and 20. And it also would split this up so that that point at altitude would intersect at the circle's center. So, like I said, there's a lot of trig that would be involved here. I would need to use, the sine of 20 to find the radius here. I'd have to use cosine of 20 to come up with what the altitude was itself. Once I had those two values, I could find the area of the circle. I could also find the area of the semicircle. And then at that point, it's an easy concept. It's just simply area is just going to be the area of the triangle plus the area of the semicircle. So in respect to the process, it's an easy concept. It's just that to get the numbers, it's involved. You got to use the trig here. So I don't want to waste our time because, like I said, the Regents exam is not going to have something this extreme to it. But again, if you want to challenge yourself, by all means, go for it. And if you do want to give yourself a challenge, I will tell you that the answer would be approximately 37.5 units squared. So feel free to give yourself a chance to try that one. But like I said, it's sine of 20, utilize that to find this side, cosine of 20 to find the red side, and then plug it into the formulas. All right, looking at the next example. This is area of a sector. So area of a sector, like, is basically just a portion of the circle, a sector, a section, or a portion. So we really just need to know, utilize our area formula, which we know is area equals pi r squared. So in this example, the radius is 10, right? They gave it to us here in the picture as well. So I got pi times 10 squared. So we know that that's 100 pi, right? And if they wanted a decimal answer, they could. But in this case, in terms of pi, it's fine. So what if I said to you half of that circle, right? I know all of you are smart. You would just take that number and simply divide it in half. Well, then the area equals 1/2 pi r squared, right? Or simply divided by 2. So that would be 1/2 of whatever the area was, which we already found out to be 100 pi. So now we know my answer is just 50 pi. And if I said a quarter of a circle, right? Well, that's area would be 1/4 the area of the circle. So again, that would be 1/4 of what we already know to be 100 pi from there. For some reason, it's getting a little sloppy here. 100 pi. So it's just simply a concept of just taking what you know and just multiplying by the fractional part here. So this would be 25 pi, right? So if that's the case, then what happens when I have something that says defined by a central angle of 60 degrees? So now they're saying here, if I look at the picture, what happens if I don't come out with a half or a quarter? What if I specifically come an amount of 60 degrees? How much is this? How much is this section here, right? Again, it's just the same like we did here with the fact that I've got, a portion or a fraction of the amount. Same thing here. What fraction of that is the whole? Well, in a circle, the whole circle is how many degrees? It's 360 degrees. So I simply take the 60, divide by 360, right? That is our fractional amount. And then, just like all the other ones, we're going to just multiply that by whatever the area was. And the area of the whole thing was 100 pi. So in this problem, we now have this coming out. And 60 out of 360 is just a sixth. So now it's a sixth of 100 pi. And a sixth of 100 pi would be 100 pi divided by 6. Which I can simplify because 2 goes into both of them. So that would be 50 pi over 3. So that would be the value. Again, I could find the decimal equivalent of that and round it off if I needed to, but that's your area in terms of pi. So really, what did we do there? What happens if I start changing and changing this degree? So we can create a little formula here. So jot this down. All right, we can have here. So the area of a sector is simply just going to be the arc degree, or the angle degree, whichever way you want to describe it, it's the same thing, over 360 times the area of a circle, which is pi r squared. So that's all our formula is. So that fraction here, and again, it works with a quarter, it works with a half, right? Whatever the angle is, like let's say it was 90 degrees, right? 90 out of 360 is 1/4, aka a quarter of a circle. Or as I say half, well, half of a circle is 180 degrees. So 360 and 180 over 360 is just a half. So whatever that amount is, whatever that angle or that degree is, we just simply divide it by 360. That gives us the fraction of the circle we're talking about. And we simply multiply that by the whole thing, and it tells us what that portion is. So if you look at example 6, we're going to utilize the area of a sector, but they made this even a little bit more because now it's not just the whole sector, which would be this part here. That's the sector, right? The wedge, so to speak. But now it's just the blue part. What's that portion alone? So this is like the area of a shaded region part along with area of a sector. So the area of the shaded is going to equal, in this case, the area of, I'm going to just write sector here, minus, right, the area of a triangle, right? So if I remove this green triangle here, that would just leave me the blue part. So let's actually solve that. So area of the sector is going to equal, we know that the angle is 90 degrees. Now again, they could give it to us here, or they might write it out here like this and say the arc is 90 degrees. It's the same thing. So we're going to say 90 out of 360 times pi r squared. So pi, and the r in this case is 5 squared. So 90 out of 360 is just a quarter times 25 pi. So that, again, I could get a decimal, but for now, let's just leave it in terms of pi. So that's just 25 pi over 4. So I'm just going to keep that here for now until I actually plug it into the calculator. And we got to find the area of the triangle here, which, again, this is a radius of 5. And this is also a radius. So again, anytime you have a radius in a circle, that has to be the same. So this is also going to be 5. So 1/2 base times height is going to be 5 times 5. So 1/2 of 25 is 12.5. So now I'm subtracting 12.5 from that answer. So now that I have all the information, now I'm going to go back and actually plug that into the calculator. So 25 pi, and if I divide that by 4, that's going to get me a decimal of 19. Let me do it and keep it the colors consistent. That's going to be 19.634954 blah 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 blah. I'm going to subtract the 12.5 from that. When I do that, I get an answer of 7.13495 blah 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 blah. It tells me to round to 1 decimal point, so that's approximately 7.1. Again, no unit measure, so just units squared. So, like I said, it's now we're just kind of putting everything together here. We've got the ability to, solve those missing this shaded region by just doing the section or the sector of it, and allowing us to, just remove the portion that we don't need to find that area. The other thing is, and we'll see other examples like this. This is referred to as the minor arc. I could also be describing something to you like with all of this. This would be the other portion, or the major arc, which is the same thing as this degree. So the what's left over, like what's the remaining part of the 360 in this example would be like 270. So if they wanted maybe like this section, you could, but they told you this angle, you could say, the other part of that is 270, just 360 minus 90, which gets me the 270. So you can sometimes see things like that that'll also, require you just maybe an extra step to find the degree or the angle. So, but take the opportunity and try these on your own, and if you we'll work on them and then give some practice problems to try it on your own.